All right, we are now going to start chapter 4, which is integration. We're going to start off with section 1, antiderivatives and indefinite integration. We'll find out what all those words mean. So, I don't know why I have a blank page. For each derivative, I want you to determine a possible function. All right, that's what your exploration is going to be. So for this first one, if the derivative of the function was 2x, well then my original function, f of x, had to be something like x squared, because the 2 comes down in front, right, and becomes 2x. But I could also have something added on the end, because the derivative of that 7 would be a 0. The derivative of this function is 2x. Okay, so if the derivative is x, well, to get an x in it, I'd have an x squared. But I'd bring down the 2, so to get a coefficient of 1, I need a 1/2 in the front. But I could also add a number. To get a derivative of x squared, that means I would have had to have had an x cubed in my original. But when I bring down 3x squared, right, when I take that derivative, I want that 3 to go away, so I need a 1/3. I don't know, there might be a number on there too. All right, if the derivative is 1 over x squared, well, to get an x squared in the denominator, we started with a 1 over x, right? The derivative of that is negative 1 over x squared, though, so we got to offset that negative. Maybe I'll subtract 7 this time. If my derivative is 1 over x cubed, my original function would have had a 1 over x squared in it, and we would have brought down in front a negative 2. So to cancel out multiplying by negative 2, we'll multiply by negative 1/2. And maybe that one doesn't have a constant. Who knows? And then if the derivative was cosine, well, the derivative of what function is cosine? The derivative of sine. So our original function was sine of x. Maybe it had a -1. Who knows? So that is an antiderivative. An antiderivative of a function is the function that would have given us that derivative. So if the derivative of f is equal to lowercase f of x, the function capital F is the antiderivative. So for example, to find a function f whose derivative is 3x squared, you could conclude that capital F of x was x cubed because its derivative was 3x squared. An important note here, f is an antiderivative, not the antiderivative, because there could be a plus number. So if f is an antiderivative of lowercase f on an interval I, then g is an antiderivative of f on an interval if and only if g is of the form g of x equals f of x plus c for all x in I, where c is a constant. Basically, that means at the end of an antiderivative, always include plus c, because there could have been a constant and we don't know sometimes. Sometimes we know. We'll talk about that. So a little bit of vocab. The constant of integration, that's that c that we added on the end of our antiderivatives. The general antiderivative is the family of functions represented by g, where g of x equals f of x plus c. The antiderivative plus c, that's the general antiderivative. The general solution is just g of x equals f of x plus c. And differential equation in x and y is an equation that involves x, y, and derivatives of y. There's no derivatives of x in there because they should be 1. So let's find the general solution for the differential equation y prime equals 2. Well, if my derivative is 2, then my original function was a 2x at some point. But there could have been a constant, so always include that plus c. And there we go. To solve differential equations, we write it in differential form. the derivative of y equals f of x dx. We always basically take our dy dx and we move the dx over to the other side, just like we would with fractions, because it tells us that x is the derivative, or is the variable that we used for the derivative. Y is that other variable. So antidifferentiation and indefinite integration, same thing. The operation of finding all solutions of a differential equation. It is denoted by this kind of funky looking S-type thing. So we write it as y, whatever our antiderivative is, equals the antiderivative of f of x, we call that the integrand, dx. That's your variable of integration. You always have to label what the variable of integration is. Always, always, always. It's not correct without it. And that'll equal capital F of x, which is an antiderivative of lowercase f of x, plus c. Don't forget that plus c. It's very common for people to forget the constant of integration. So, antiderivative of f with respect to x. That's what that means. dx means it's a differential, and that identifies that x is the variable of integration. If I had a dt, that means t was the variable of integration. It's just like when we took derivatives. If I took a derivative of t, I may have needed a dx dt in my function. X has to identify that is the variable that we took the derivative of. So some basic integration rules, which you will fill in. The antiderivative of a derivative is just the function plus c. Okay? The derivative of an antiderivative, those cancel each other out. Derivative and antiderivative undo each other. Boom, we're left with what was inside. So some differentiation formulas. We know that the derivative of a constant is 0, which means the indefinite integral of 0 is a constant. We know the derivative of a constant times x is just that constant. So that means the antiderivative of a constant is the constant times x plus c. We know the derivative of k times some function is k times the derivative of that function, which means if I have a constant times a function in my antiderivative, I have k, my constant, times the antiderivative of the function. We know when we take a derivative, we can add and subtract the derivatives of separate pieces. Same thing works with integration. We can split them apart and do my antiderivative separately. So derivative of x to the n power is n times x to the n minus 1. Remember, we bring down the exponent and we subtract 1. So that means the antiderivative of x to a power is x to the power plus 1 divided by the power plus 1 plus c. Don't forget the c. The derivative of sine is cosine, so the antiderivative of cosine is sine of x plus c. The derivative of cosine is negative sine of x, so the antiderivative of sine of x is negative cosine of x plus c. The derivative of tangent is secant squared, so the antiderivative of secant squared is tangent of x plus c. The derivative of secant is secant x tangent x, so the antiderivative of secant x tangent x is secant x plus c. The derivative of cotangent is negative cosecant squared of x, so the antiderivative of positive cosecant squared of x is negative cotangent of x plus c. And the derivative of cosecant of x is negative cosecant of x cotangent of x, so the antiderivative of cosecant x cotangent x is negative cosecant x plus c. These are all just opposites to point out to you the patterns. So let's find a general solution of the antiderivative of 3x dx. All right, well, anytime I have an x, I know it's going to become an x squared over 2, right? I take my power, add 1, divide by that power. But we still have that 3 on the front, and we need a plus c. That doesn't look like how we'd ever leave it, right? Maybe I'll go 3 over 2, x squared plus c. There's my general solution. Sometimes it's helpful to rewrite our integrals before we actually try to do them. So I have 1 over x cubed dx. I would rewrite this as x to the negative third power dx, because now I can follow that general power rule. So I'm going to add 1 to my power, make it negative 2, divide by that new power, and plus c. Well, that means we have 1, plot my negative up per top, over 2x squared plus c. There's my general solution. The antiderivative of the square root of x. Well, that's x to a 1/2 power dx. So I add 1 to my power, 3/2, and divide by that new power, plus c. Well, dividing by 3/2 is the same as multiplying by 2/3. X to the 3/2 power plus c. And 2 sine of x dx. Well, we could take that 2 out front. Antiderivative of sine of x dx. Well, the antiderivative of sine of x is negative cosine of x plus c. Notice that the plus c can just hang out on the end. I don't have to put it all in parentheses when I took that 2 out front. Negative 2 cosine of x plus c. Because 2 times c is just a new constant that I don't know yet, so it's still just a c. All right, the antiderivative of dx. This one's tricky because remember that there's always an invisible 1. So that's just a constant, which means it's the constant times x plus c. Antiderivative of x plus 2 dx. Remember, we can split that apart into the antiderivative of x dx plus the antiderivative of 2 dx. The antiderivative of x is x squared over 2 plus c. The antiderivative of 2 is 2x plus c. We can just put a single plus c on the end. Because one constant plus another constant makes a new constant. We don't know what that constant is anyway. Just put 1 plus c at the end of your antiderivatives. All right, for part c here, we will break it apart. Antiderivative of 3x to the 4th power dx minus the antiderivative of 5x squared dx plus the antiderivative of x dx. Remember, we can take those constants out front too, so 3 times the antiderivative of x to the 4th power dx minus 5 times the antiderivative of x squared dx plus the antiderivative of x dx. So when I find my antiderivative, I have 3 times x to the 5th power divided by 5 minus 5 times x cubed divided by 3 plus x squared divided by 2 plus c. Don't forget your plus c on the end. And, oops, sorry, I would rewrite this a little bit. I'd make it 3/5 x to the 5th power minus 5/3 x cubed plus 1/2 x squared plus c. There's our antiderivative. And now we're going to get a little more wonky. Let's actually rewrite this. Oh, hey. Let's make it x over the square root of x plus 1 over the square root of x dx. Because remember, you can break a numerator apart like that. So we really have the antiderivative of x over the square root of x, which is actually square root of x dx, plus 1 over the square root of x. Well, that's x to the negative 1/2 power. Ooh, I should probably rewrite the square root of x also. So that's the antiderivative of x to the 1/2 power dx plus the antiderivative of x to the negative 1/2 power dx. If you're wondering how I made this jump, remember that it's x to the 1st power over x to the 1/2 power. Whoops. And remember that we subtract those exponents, leaving me just an x to the 1/2 power. All right, so we add 1 to the exponent, so that's 3/2. Divide by that new exponent, plus add 1 to the exponent, that's 1/2. Divide by the new power, and plus c. So we have 2/3 x to the 3/2 plus 2x to the 1/2 plus c. And there we have it. Now we have sine over cosine squared. This is a little tricky because we have to rewrite it. Oh, hey. We know that sine of x over cosine of x is something special. that leaves me a 1 over cosine of x left, dx. Sine over cosine is tangent. 1 over cosine is secant. We have a rule that says the antiderivative of secant tangent, well, that's the same thing. So this is actually secant of x plus c. All right, now we're going to get crazy. The antiderivative of 2 over the square root of x. I would rewrite this. This is the antiderivative of 2x to the negative 1/2 power dx. The 2 can come out front. So then we get 2 times x to the 1/2 power, because I add 1, divided by 1/2 plus c, which is 4 square root of x, because x to the 1/2 power, plus c. And there we go. For b, this antiderivative, well, let's multiply that out. T squared plus 1 times t squared plus 1. So we have the antiderivative of t to the 4th power plus 2t squared plus 1 dt. And then we'll separate that out, t to the 4th power dt plus 2 antiderivative of t squared dt. I just took that 2 right out front right away, plus the antiderivative of 1 dt. All right, well, the antiderivative of t to the 4th power is t to the 5th power over 5, plus 2 times the antiderivative of t squared is t cubed over 3, plus the antiderivative of 1 is t plus c. And we'd probably want to make that 1/5 t to the 5th power plus 2/3 t cubed plus t plus c. All right, letter C here looks a lot crazier than it really is. We want the antiderivative of x cubed over x squared plus 3 over x squared dx. Right? I just broke that fraction apart, which is really the antiderivative of x dx plus the antiderivative of 3x to the negative 2nd power dx. Antiderivative of x is x squared over 2 plus 3 times the antiderivative of x to the negative 2nd power is x to the negative 1st power divided by negative 1 plus c, which is 1/2 x squared minus 3 over x plus c. And the cube root of x times x minus 4. Ooh, that one looks terrible, but we can make it much easier. Distribute the cube root of x. Remember, cube root of x is a 1/3 power. 1/3 times x to the 1st power makes x to the 4/3 power minus 4x to the 1/3 power dx, which we break apart into x to the 4/3 power dx minus, I'll bring that 4 out front, x to the 1/3 power dx. Antiderivative of x to the 4/3 power dx is x to the 7/3 power divided by 7/3 minus 4x to the 4/3 power divided by 4/3 plus c, which makes this 7/3 x to the, 3/7 x to the 7/3 power minus 3x to the 4/3 power plus c. All right, and then we have something called a particular solution. A particular solution is an antiderivative in which you know the value of the constant. We know that value of the constant by using an initial condition. It gives us the value of y equals f of x for some value of x. So what will happen is we want the general solution of f prime of x equals 1 over x squared if f of 1 is 0. So basically, we take the antiderivative of 1 over x squared dx, which is the antiderivative of x to the negative 2nd power dx, which gives me x to the negative 1st power divided by negative 1 plus c, which is negative 1 over x plus c. But we know f of 1 equals 0. So that means if I plug in 1 for x, I should get 0, which means negative 1 plus c is 0, which means c is 1. So I know my function, f of x, is negative 1 over x plus c, which is 1. All right, and a nice little application problem to round out our day. A ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Assume the acceleration is a of t equals negative 32 feet per second per second. Find the position function, giving the height s as a function of the time t. Now it's important to remember that if I start with s of t, the derivative of the position function is the velocity function. And the second derivative of position, which is the derivative of velocity, is the acceleration. So I know my acceleration function was negative 32. So the velocity function can be given by the antiderivative of the acceleration function with respect to t, which is the antiderivative of negative 32 dt, which means that my velocity function is negative 32t plus c. But we know the initial velocity is 64. That means v of 0 is 64. So I know v of 0 equals 64. So that's negative 32 times 0 plus c. So c is 64. So my velocity function is negative 32t plus 64. But that's not what I wanted. It wanted the position function. Position is the antiderivative of velocity then. So s of t equals the antiderivative of v of t dt. So that's the antiderivative of negative 32t plus 64 dt. So the antiderivative of negative 32t, s of t, would be negative 32 times t squared divided by 2, plus the derivative of 64 is 64t plus c, which is negative 16t squared plus 64t plus c. But we also have that initial condition. We know the initial height was 80. That means s of 0 equals 80. So if s of 0 equals 80, then we know negative 16 times 0 squared plus 64 times 0 plus c is 80, which means c is 80, which means our position function is negative 16t squared plus 64t plus 80. Dang. All right. When does the ball hit the ground? Well, the ball hits the ground when the position function equals 0. Well, let's divide out our GCF. Let's divide everything by negative 16. We get 0 equals t squared minus 4t minus 5. I can factor that. T minus 5, t plus 1. So t is 5 and t is negative 1. Well, time can't be negative, so it hits the ground after 5 seconds. So now you have an assignment to practice your antiderivatives.